So not all differentiable equations can be solved. And right now, we can only solve separable first order differential equations. So that means we only have first derivatives involved and the x and y components can easily be separated so the x's are on one side and the y's are the other. But there's a whole world of differential equations and different kinds of them. There's ordinary differential equations, there's partial differential equations, and they all have their own solving techniques, and some of them just aren't solvable. Um, so when we can't solve a differential equation, we can still glean a lot of information out of it. So one way that we can glean a lot of information is by generating a slope field, which can kind of give us the graphical solution to it and kind of show us the visual trends over time and kind of how the solution curves might look. And these are great visuals, but they're only really good for getting the general trends in the solutions and for long-term end behavior. But sometimes we want to know a more specific result and we want to do a numerical approximation. We want to be able to kind of find an approximation for a function value even if we can't find the actual solution curve, right? We can't find the equation of the solution curve. So one of these numeric solutions, these numeric methods that we can resort to is called Euler's method. So Euler's method or Euler's method, however you want to say it, is a numeric approach to approximating particular solutions to a differential equation, and it uses the idea of local linearization. So that's the idea that we can write a tangent line for a small interval of time and use that tangent line to approximate the next y coordinate that we want to know. So the emphasis here is that we can use short tangent lines over short distances to approximate solutions given some sort of initial value, right? So in other words, a short distance, right? So we have a small delta x, right? So you're not going to be approximating changes over like even a whole number step, right? We're not looking at that big of steps. We want to look at small changes. So we're going to rely on the idea that close to a point, a function and its tangent line do not differ by much, right? If you graph a curve, say on Desmos or your graphing calculator, and then you graph the tangent line to a point on that curve and you zoom in really far, right? The tangent line and the curve are pretty similar on your screen. There's not a whole lot of difference between them, especially if you zoom in really close around that tangent point. That point of tangency, rather, if you want to say it with proper verbiage. Right, so we can use this idea that the tangent line and the function are very similar to each other over small distances to do Euler's method. So the two things that we need in order to do Euler's method to find a numeric approximation for a solution to a differential equation is we need to know the differential equation, so they have to give us the dy dx equals. So here it's written as y prime equals a function of x and y, right? So basically we need to know dy dx, and you need to know an initial condition, which we're going to label as xo, yo. You can also say x naught, y naught. That's our initial point. So if you know these two pieces of information, you know that the graph of the solution, if we could find the particular solution curve, you know that it's going to pass through the initial point x naught, y naught. Right? It's definitely going through that initial condition that they give you. And you know the slope of the tangent line is dy dx evaluated at the point x naught, y naught, right? You can find the slope at that point and you know that that point is definitely on the curve. So what Euler's method involves doing is we move from the starting point x naught, y naught along its tangent line by taking a really small step to a new point, and then we do this process again. Once we step to that new point, we draw another tangent line, we make another tangent line approximation, and we just keep stepping until we get all the way over to the point we're trying to actually approximate. So this stepping process is called iteration or iterating, and we just keep going until we go from the initial point to the point that we're trying to approximate. Because we might, like if we know, say that the curve passes through 1, 2, we might not care what happens at 1.1, but we might care what happens at 1.5, so we might have to take multiple steps to get there. So visually what's happening, right, say we have a curve going on. I'm going to draw a little xy axis. So say we have some initial point right here. So this is x naught, y naught, right? So my y coordinate here is y naught, and then x naught. So we're going to draw a tangent line at that point. So say we draw a little tangent line, say our dy dx gives us that this is the tangent line. Okay, so I have some delta x. So say I have my delta x here, So I'm going to get a new x-coordinate at x naught plus my delta x. So if I go up to my tangent line, right, and we'll let that equal our x1, right? It's our next x-coordinate. We're just going to use different subscripts to iterate and kind of show the progression. So there's my new x-coordinate, which means my new y-coordinate is over here, and I'll call that y1. So if we're thinking about this in terms of a very small change, right, I had to go over and up from my initial point, right? You can think of it in terms of a right triangle. So I went over a delta x amount, and the delta x is normally given to you, so it's like take steps of like 0.1, 0.01, 0.5, or you know how far you want to get to, and it's kind of like when we did Riemann sums, right, your b minus a over n. So say you want to go from x of 2 to x of 3, and you want to do it in 5 steps, right? You would do 3 minus 2 and then divide it by 5 to get 0.2, that kind of deal. But we also have, right, we have this delta y component too, right? So we go over an x amount and then we go up a y amount. But how is that delta y figured out, right? Because the delta x amount is usually given to us, right? How big are the steps we want to be taking? So if we think about it, the slope of this tangent line, right, we'll let this, like, we're going to let dy dx at the point x naught, y naught. That's just our slope of the tangent line. So I'm just going to let that equal n. If you want, you can make it m0 if you want to make sure that you know it's at that point. So I know that if that's the slope, we know that from like algebra 1, we know that the slope of a line is really equal to the change in y over the change in x. Right? Because now we're just looking at this in terms of a linear equation because we're only drawing a tangent line. So if I solve this equation to find my dy, right, this tells me that my delta y is equal to my slope, which is my derivative value, times my delta x. So my y1 over here, I don't want to show this, my y1 that I labeled over here is actually equal to my initial y-coordinate, y0, plus m times my delta x, right? And so say now I'm at this new point and I draw its tangent line. So say its tangent line looks like this. And I move another delta x over, right? And I go up. Apparently I didn't draw this line long enough. There we go. Right? Now I get this y2. And so same thing here. If I make my little triangle here, right, I have a new delta y and this same old delta x, right? And this delta y is going to be equal to the slope at that previous point. So this is the slope at x1, y1 times my delta x, right? So this is still equal to the previous y value plus the slope at the initial value times my delta x. So you can kind of start thinking about it this way, and then if we draw a solution curve, right, if we actually could find the initial solution curve, we would find that these tangent line approximations aren't usually too far off of the real curve. They're usually good approximations, especially if you're using a tiny delta x. So we could keep going with this and keep making more steps, right? I'm just making up a graph because we don't know what the slopes are. So literally just making up a graph. Doesn't really matter. Right, so all we're going to be keep doing is using these little tangent lines, like these little triangles, to keep kind of stepping around our curve and getting better approximations for the next y-coordinate. So what this kind of boils down to is that I'm going to write this first in like more mathy symbols, and then we'll write it in like normal people speak, right? My next y-coordinate, so my I plus 1 y-coordinate is equal to my ith y, so my I-coordinate plus the derivative evaluated at xi comma yi, right, times my delta x. So what this is kind of like our Euler's method formula to approximate values, right? So what this really boils down to here is y sub I plus 1, that just means the next y coordinate or the new y coordinate, right? So my new y is equal to the previous y coordinate, which I could spell today. My brain is still a little scrambled. My previous y plus the slope at the previous point, right, times my delta x, times my change in x, right? So as long as you know a point and you can find the slope at that point, you can get to the next x and y coordinate. And so let's look at how that actually looks. So you can tell that I have my TI-84 pulled up on my laptop. You don't have a calculator handy, probably want to grab one just to follow along. So I'm going to actually copy this little formula down onto my next page so that way we can think about it while we use it. Okay, so if we're told in this example, if dy dx equals 2x minus y, and if y equals 3 when x equals 2, we want to use Euler's method with 5 equal steps to approximate y when x is 1.5. So let's make sure that we can pull out all of the initial kind of stuff that we have. So we know our dy dx equation is 2x minus y. So that was one of the things that we needed to be able to have in order to use Euler's method. We also know my initial condition, right? So our x naught, y naught is the point 2, 3. And then we need to figure out our delta x. So we want to go to 1.5. So my delta x is going to be, would help if I put the x there, 1.5 minus 2. So my end goal minus where I'm starting, all over my 5 equal steps. So that's going to be negative 0.5 over 5. So I'm going to take steps of negative 0.1. So your delta x can be negative, so you can start somewhere and go to the left. You don't have to go to the right. So I kind of like to do, it's not like a table, but I kind of like to use lines. So I like to work vertically so I know where I'm going. Okay, so my initial point, and I want to do this 5 times. So my initial point is 2, 3. Okay, so my next x coordinate, right, is going to be 2 plus negative 0.1, so that's going to give me 1.9. This is like step 0. This is going to be step 1. Okay, so to find my new y coordinate, I want to do my y equals my previous y coordinate. So my previous y coordinate is 3 plus my slope at the previous point. So dy dx evaluated at the point 2, 3 times my delta x. Okay, so that's going to be, and I'm just going to do that on my calculator. So I'm going to switch over here so we can see the calculator fully. So the way I like to do this is I like to be able to copy things down and not have to change a ton between iterations. So I'm going to hit my first y coordinate and hit enter. So my next y coordinate has the formula of my previous answer. So I'm going to do second answer to pull that up. Plus, I want to plug in my slope. So my slope is always going to be, according to this formula, it's 2x minus y. So I'm going to do 2 times my x coordinate, and I'm starting at 2.0. And I'm typing it with the decimal because I know all of my other ones are going to have decimals. Minus, I know it's the y coordinate at the previous point, but my previous y coordinate was 3. So I'm going to use second answer again, and I want to multiply this by my delta x. So right here, this formula is standing for previous y plus my slope, my dy dx equation evaluated at my previous x and y coordinate times my delta x here, and then I'm just going to hit enter. So now I have, can I make this smaller? There we go. Right now I have that my new y coordinate is 2.9. Okay, so now I'm going to add my delta x again. So my next point is going to be 1.8, comma, now I want to figure out that new y coordinate. So now I'm using my 1.9 and my 2.9 as my previous y coordinate. And if you want to write it out longhand, you absolutely can. right, you could say, okay, this new y is going to be equal to my old y of 2.9 plus my derivative. So dy dx is going to be 2 times 1.9 minus 2.9 all times negative 0.1. So you could set that up on your calculator each time, type it in, and then go from there. Right? I want to do this so I don't have to do as much work. So if I go back to my calculator and make this bigger, I'm going to go up and copy down my previous line. And so when it has that minus answer, it's always pulling the previous answer. So wherever it says ANS in this line, it's pulling 2.9. So I only need to replace this. I want to do 1.9 instead. And now I get that my next y coordinate is 2.81. Okay, so then I'm just going to keep going, right? So if I find my new x coordinate, it's going to be 1.7. Right, I'm going to go back. This is really my new y is going to be my previous y, so 2.81 plus 2 times 1.8 minus 2.81 times negative 0.1. Or, right, I'm just going to go back to my calculator, copy down my previous line, and I'm just changing the x coordinate now because the ANS is going to pull the previous y coordinate for me. So that's going to give me 2.731. And I like doing this all in the calculator because that way I don't have to worry about rounding and it's using the most accurate answers I can. You don't want to round these until the very end. So then you guys can't see what I'm writing on the iPad now. Right, so if I add negative 0.1 again, right, I'm going to get down at 1.6. So I want to get that this is y equals 1, y coordinate, so 2.731 plus my slope, so 2 times 1.7 minus that, right? I'm just writing this out in case you're doing it longhand. Right, I'm going to go back over. I'm not going to do it longhand because I'm lazy, so I'm going to copy this down and just change my x coordinate to 1.7, and there we go. So now you can see I'm going to probably have to move my writing over, whoops. So 2.6641, I'm pretty sure if I remember that correctly. So see, it's 4 decimals now, and AP only requires 3, but I'm not going to round till the very end. So now I wanted to get to 1.5. So now I'm finally here, right? I'm on my 5th step. So I'm going to take that previous y coordinate and then add it to my slope times my delta x. So I'm going to just go back over to my calculator one more time. I'm going to go up and copy that down, and then all I have to do is change the the x coordinate because I already have the y coordinate being pulled down with that ANS. So my final approximation here is there we go. We got 2.61051. So that means that at x equaling 1.5, y is approximately 2.611, right? I'm going to round it to 3 decimals once I get to the very end. So let's actually look at the graphical solution of this. So on Desmos, I actually generated the slope field for this differential equation already. You can see it over here in my second line. And then this pink dot, the 2, 3, is our initial point, right? You can see it here. So I went ahead and plotted the points for all of our iterations. So after 1 step, we're here, right? 2 steps, 3 steps, right? 4 steps, and then 5. So you can also kind of see how the dots are curving, so you kind of get a general idea of what the solution curve looks like over that little window, right? So there was our final approximation. Well, I went ahead and actually solved this equation. You can solve this one if you know the methods. So our solution curve is actually right here. I'm going to zoom out just for a second so we can see the curve. Right? It's got that nice little shape to it, nice curve that follows the differential equations, the slope field. But now if I zoom in, right, really close over where the 1.5 is, put the label on that one, right, we can see that there's not a huge difference between this point and where the curve actually is. So the actual value of the curve is this g of 1.5 number. So the actual value according to Desmos for this curve is 2.64872, blah, 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 right? Keeps going on. So what I did down here is I found the error amount that we had, our actual value minus our approximation, right? So we're pretty close. We're within 4/100ths of the actual value, and that's not a bad error amount to have. So this is how Euler's method kind of works. I wanted to show you visually kind of what's happening there. Okay, so I'm going to go back to the iPad, and let's do one more problem together. And let me pull up my calculator. There we go. Okay. So two-part question here. So we're told that dy dx equals x minus 2 with the initial condition of 0 and 5. So this is a separable differential equation. You can solve it. In fact, in part B, we are going to solve it to kind of figure out how close we are. So we want to find an approximation for Euler's method, using Euler's method of 2 steps to find y of 0.8. Okay, so we know that our slope is dy dx equals x minus 2. Our initial condition, right, our x naught, y naught is going to be the 0.05. And then my delta x equals where I want to go, 0.8 minus where I'm starting over the number of steps. So that's going to give me 0.4. Okay, so I'm starting this at the 0.05, right? And I know I'm going to step through 0.4, and then I'm going to go to 0.8 using my delta x. I'm just going to set those up right away. Okay, so my dy dx here, maybe we'll write it out a little differently because this problem's not as big, it's not as complex. At 0, 5 is equal to 0 minus 2, so that's negative 2. So this y coordinate here is going to equal my previous y, so 5 plus my slope times my delta x. And so maybe I don't feel like doing math today, so maybe I go over to my calculator and do 5 plus negative 2 times 0.4. Close my parentheses. Okay, so I get 4.2 there. Okay, so maybe I also want to know what the slope is at this point. So maybe it's easier to write it out like this. My slope at this point would be my x value of 0.4 minus 2, so it's going to give me negative 1.6. Right, and then we're just going to start the problem over again. Right, so to find this final y coordinate, I'm going to do my previous y coordinate plus negative 1.6 times 0.4, and then I'm just going to type that in. So I'm going to get 4.2 plus negative 1.6 times 0.4. And that is going to give me 3.56. Right, so if I wanted to write like a little statement, I'd say at x equaling 0.8, y is approximately 3.56 using Euler's method. Okay, so in part B it says to actually solve it using that initial condition, we're going to find the actual value of 0.8, and then we're going to compare it to find the actual value. So we're going to find our error amount, in other words. So if I know that dy dx equals x minus 2, I can separate my variables by just multiplying both sides by dx and then integrating. So I get that y is equal to 1/2 x squared minus 2x plus c. So using my initial condition, I know that 5 is equal to 1/2 times 0 squared minus 2 times 0 plus c, which means that 5 is my c value, which means my curve is actually 1/2 x squared minus 2x plus 5. So y of 0.8 is actually going to equal, right, I'm just going to go over and use my calculator now. We had 1/2, so 0.5 times x squared, so 0.8 squared, minus 2 times my x of 0.8, and then plus 5. So that gives me an actual value of 3.72. So going back over to the iPad now, right, that's our actual value. And so if we want to compare it, right, our error is technically the absolute value of new minus old, or like actual minus approximate. So we're going to get that the actual was 3.72 minus 3.56. I'm too tired to do decimal math today. So minus 3.56 from that, right? So we get an error amount of 1600ths. That's not bad, right? So we were only off by 1600ths. It's not a bad idea.